Okay, here's part 2. At the top of page 3 of my thing, which is the end of the 4-3 parts of the problems for those of you in other classes who may not have the exact same version I have. Anyway, we have a proof here. Oh gosh, not a lot of room to do it though, so let's see if we can squeeze it in here. Of course, the first reason is going to be given, and that stuff is right here. Let's mark it. AB is congruent to PQ, and it's parallel. Whoops. I did like you. I screwed up the parallel versus congruent situation. Now, those two are very different for very different reasons. They're good for different. The biggest problem I'm seeing in my class is that people see the parallel markings or see this parallel thing and automatically think, oh, then I can bank that as a side in my side angle side or whatever. Parallel doesn't tell you anything about the length of the thing. This tells you all about the length of the thing, so we have it also, but a lot of times you only have this one. And the parallel thing is really good for angles. Parallel is about direction, right? So that you can kind of equate that with the angle things are moving at. So that's, or the angle things are pointed. Anyway, so we're trying to get BZ congruent to ZQ. So I'm guessing this is going to be a triangle congruence proof. I'll put it way down here because I have to skip some space. I'm guessing it's going to be triangle BZA. This is a guess. It's going to be congruent to BZA, probably QZP. Now, why did I flip the other one upside down? Because I'm thinking AIA angles with these parallels. And again, this is just a guess at this point. Because if I had that, then this comes out really easy. BZ would be congruent to ZQ. Well, here's another reason why I flipped it. BZ in one triangle has to go with ZQ in the other triangle. And if I didn't flip it around, I'd have BZ with PZ, and that doesn't work. And they kind of look like they're flipped around, right? Like B is a pointy angle and Q is a pointy angle. Pointier, I mean more acute than A and P. So B and Q are going to go together in the triangle down there. So that's why I did that. I'm pretty sure this is going to be how it works out. Right now, I only have a side in this, so I can't claim they're congruent yet. The reason here is going to be side, 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 or side, angle, side, or angle, side, angle. So far, I just have one side. It's from the given. But, of course, I have all kinds of other stuff. With these parallels, remember I said parallels are about angles. Angle B and angle Q are AIA angles. That's nice. But so are, by the same token, I'll just put them in the same step. You could do vertical, but you know what? I like saving steps here. Angle P is also congruent to angle A by AIA. So now look, I got angle side angle and I'm done. Step 3, step 4. I could have done verticals. I would have had angle side. That's fine. There's nothing wrong with that. But I'm done this way. Okay. Oh, a good problem on the test might be someone does this with angle side angle. Someone else does this with angle side. What was different? One of them used vertical angles, the other one didn't have to. One of them used AIA twice like I did, and the other one used it once. Okay, BC is congruent to DC. That stuff is given. And angle 3 is congruent to angle 4. So I'm supposed to, whoa, AC is a bisector. Bisects a bad angle. Okay. Angle BAD. Well, that's basically like having to prove that angle 1 is congruent to angle 2, because that would be the definition of, I'm not leaving myself much space to put the numbers in. Definition angle bisector would say that, yeah, that's true. Okay, so what I'm headed for, and notice I skipped some steps. This is the end. 1's congruent to 2, which would be true if angle ABC, you see my style now? I like going backwards. ABC is congruent to ADC. So now this is at the top of my wish list because then this comes out nicely. Remember, this is a side angle, side angle, side angle, something. I have an angle and a side right now. So I need one more piece. Oh, look, reflexive. It's going to give me side angle, side. These things write themselves backwards sometimes. It's great. Okay. And what was it? It was AC. 2. Okay. You can read that forwards. Pause now, read that forwards, and it should make sense to you. Okay, now we're on to the 4-4 stuff. This is where we start meeting isosceles triangles for the first time. So, whoa, what am I doing here? Hard to scroll while I'm talking. Just a second, let me find it. And we're back. Okay, refer to the figure in example 1. Well, this time I was smart and I actually included example 1. Given 2 congruent segments, name the isosceles triangle and the 2 congruent base angles. I call that theorem the isosceles triangle base angle theorem. You might see that. Other teachers might call that the isosceles triangle theorem about angles, because the thing you're trying to prove there is that if two sides are congruent in a triangle, it proves that yes, you're also going to have two congruent angles. It's this way. The converse of this is true. That would be either called ITT sides or it-back converse, but we're dealing with the straight ahead one here. Looks like example 2 is about the converse. All right, example 1, if AC is congruent to AD, then the isosceles triangle we're talking about is ACD, and the angles that are congruent would be angle, well, it's the angle at C, but I can't really say angle C, there's too much junk there. ACD is congruent to ADC, okay? In number, oh, that's a C. In number 2, I'll just leave some space. AF, ooh, is this one, and AG is that one. It looks like AFG is our isosceles triangle with angle, well, it's the angle at F. AFG is congruent to angle AGF. Okay. See how that always works? You just rearrange letters in the triangle, where the vertex is probably always going to be first. A base angle and then the other base angle, and switch them around. That's it. All right, BC, this little guy, and CF. Oh, we have a little isosceles triangle over here. Oh, I didn't need to draw that. That's kind of cool. All right. BCF, and it's the sides. If it's BC and CF, C is written twice here, so C is the vertex. So we're talking about angles at B and F. CBF and CFB. And number 4, GD and DE. D is probably the vertex. It's exactly the same thing. It's just over here. Really? You're going to make me do that? All right. GDE with, that's an E, with the angles are going to be congruent at G and E. So angle DGE and DEG. Okay. Next example is, guess what, about the converse. Converse is true if you have two angles that are congruent in a triangle. Then you can prove, so like if this, then this. You can also call this ITT sides. Okay. STU is congruent to SUT. That's this angle here and this angle here. I'm going to draw in here because I got to do 4 more problems. If those are the two congruent angles, what's the triangle? Well, the triangle have to have, well, look at this, STU and SUT. It's probably triangle with those 3 letters in it. Now, it doesn't always have to be. It depends how they name the angles, but I think it's going to be like that in here. Oh, and I want sides. The sides that are congruent in that triangle, STU, it's angle T and angle U, they're the same. So S is the vertex. ST is congruent to TU, or those lengths are equal. Angle V, okay, that's nice, is TWV, which is this one here. So we have this little isosceles triangle here. Triangle TVW, and it was V and this one at W that are congruent, so T is the vertex. So triangle T, actually you don't have to name it, do you? Oh, yeah, you have to name the vertex. You have to name that. I did the triangle. You have to name the sides. So it's TV and TW. UTZ is this angle in here, is congruent to TUZ, which is the angle in here. So the triangle is triangle Z. And Z is the vertex, so it's ZT and ZU. And the last one, XWZ, XWZ, and WZX, this little tiny one in here. I drew on it again. Z is the vertex of triangle ZWX. That one is, those problems are probably easier than test problems, actually. I can just hold that, makes it so much easier. All right, find the value of x. I don't have a lot of room to do this algebra, but I'll try. So in all these, we have an isosceles triangle, it looks like. Yep. And if you have congruent angles, then you know the sides opposite them are congruent. So here I know the 3 x minus 2 equals that. So in my head a little bit, I know that's dangerous to do. 3x minus 2 equals 16, so 3x equals 18. You know what? I'm not going to do this in my head. I'm going to write that down. 3x is 18, so x is 6. Here, I've got the 180 thing going on. If this is 65, it has to be congruent to this one because we're in an isosceles triangle, so that's 130. So I'm left with 50 here to make 180. And that's pretty much the 2 different types of questions they're going to have to ask you. Let's see. I mean, there's a little bit tricky here at the right angle or the exterior angle outside, but that's kind of how it goes. Oh, and they flip it around a little bit. Ooh, crazy. All right, these 2 are equal because we have congruent angles there and there. So 5x equals x plus 20, or 4x equals 20, so that means x is 5. You can put them back in and check. Both are 25. Oh, and here, both should be 16. Yeah. Here, if this is the 80, be careful. These are the two sides congruent, so these are the two angles that are congruent. These two have to add up to 100. So that's 100 degrees total. So the x has to be 50. This is like a total. They're not each. Sorry. I should say total. Someone's going to look at this later, think I'm an idiot. Okay. 3x, x. Oh, and guess what? These have to be equal, so this is also x. So I could say all of these, which is 5x, has to add up to 180. The trick here is that that's not going to work unless these two are the same. So x is, what is that, 36. That should have to 180. You can test that. This is 100 out here, which means this one in here is 80. This one in here is also 80, so these are 80 each. So that altogether is 160. This has to be 20 to make the 180. This, of course, is 90. These are the same because that's the isosceles triangle, so each one of them is 45. Here, oh, I'm looking for the outside angle. Tricky. This is 50. These have to be the same. I've seen that triangle before. They're both 65. You can subtract from 180 subtract the 50 from 180 divided by 2. If this is 65, then on the outside we have to add up to 180, or just add these two actually from your exterior angle theorem, and that's 115. Okay. I got some more time. Let's how about 17? Given that BC is congruent to AC, measure angle 1 is 140. Find 2, 3, and 4. Oh, this is not a proof. Given makes me think proof. Well, 140 has to equal these two added up. You're probably not thinking that. You're probably thinking if this is 140, this one has to be 40, which is right. And then we have an isosceles triangle here, and these two are the same, and they have to add up to 180 with this. So I have 140 total for these. So each one of these is half of 140, so it's 70. Okay, find the value of x. This is an isosceles triangle. This is an isosceles triangle. I'm guessing it's going to be 70, but I'll show you why. If that's 70, these two have to add up to 180, so they're 110 altogether, so each one's 55. This one's vertical, so it's also 55. Oh, look, we're in a new isosceles triangle, also 55. 55 and 55 is 110, so guess what? It's also 70. This is 62, and we have, just a second. I got stumped there for a second because I didn't notice this. Those are not at the end of the line. They're right before the end of the line, which means they're parallel markings. So, yeah, these two are parallel. So we have these transversals and all kinds of stuff going on here, which really helps. So this 62 here is AIA with this angle down here. And, of course, we're in an isosceles triangle. So that's also 62. And then I can figure out this. It's 180 minus, what is that together? That's 124. From 180 is almost 60, something like that. So then I can figure this part out with the 180 in this. That's 110, 118, 120, 62. I think I did that math correctly. Hopefully those add up to 180, and this adds up to 180, and those are the same. That's good, and those are the same. I did my geometry right. I may not have done my arithmetic right, but I think I did. Okay. I got about a minute left. Let's see if I can do something else here. Whoa, complete. Oh, I lost it again. Yeah, I think I can finish this for now. Okay, AB is congruent to CB, AB, CB. Ooh, look, isosceles triangle. And AD and CD. Great. Ooh, make sure that's not the same marking. All right, of course, that's given. All right, we're trying to prove. I'll give you a plan. We're trying to prove that BAD, basically angle 1, is congruent to BCD. Oh, sorry, BAD is angle 2 and angle 4. Okay, great. Can I just call that angle 2 and angle 4? BAD. No, it's not angle 2 and angle 4. It's the whole big thing. It's this whole gigantic thing out here. Is that congruent to this whole gigantic thing out here? Okay. I hope this is not an angle addition proof. I hate those. All right, but looks like it's going to be. 2 is congruent to 4, or you can say it that way. And 1 is congruent to 3. Well, both these are isosceles triangles, remember? So this is the one that if the sides are congruent, then the angles are congruent, which is that, or you can call it ITT angles. We're trying to prove angles are congruent. So let's mark all that stuff. That's congruent to that. That's congruent to that. Can't see the angle numbers anymore. 1 plus 2 equals 3 plus 4. Oh, great, it is angle addition. Well, 2 is congruent to 4 and 1 is congruent to 3. I just added those straight down. That's the addition property of equality. It's just an algebra step. Why is BAD equal to, I'm going to say it's equal to that, and BCD is congruent to that. Then I can say that what we want here. Yes, this is my friend, angle addition. which just basically tells you how you can add angles together when they're sitting together like this. Not very test-like. Okay, see you in the next part.